Welcome everyone to the session about the SEP NLG 2021 share task. Thanks a lot for coming and participating. My name is Don Tukuner. I'm the co-organizer together with Ahmad Aga Brahimian. I'm first just going to give a brief intro or overview of the task so that everyone is familiar with it. I'll keep it short and then we'll go through the presentation of the participants. Our idea was to get an overview of what the teams did. And then at the end, it would be great to have a discussion about the task in general or some feedback of the participants or discuss future work or future iterations of the workshop. All right, so briefly, what was this task about, or what was the motivation to do this task? So basically, in any natural language generation system, you are bound to have some noise in the text that you generate. In our use case is readability of transcripts. So we have audio recordings of interviews and discussions. We run them through a speech-to-text system, and then we would get something like this. So it's just a stream of tokens. There is a period at the end, but obviously there are other constituents in this stream of tokens that should be punctuated. And so that's basically our use case to have a post-processing component in a speech-to-text system that is able to correct or improve, let's say, the transcription of audio recordings of meetings and interviews. Obviously, there are other use cases. So let's say you want to use your transcribed speech for downstream tasks, such as machine translation and so forth. So you basically would want to do something to augment or improve the quality of the transcripts that you get or the output that you get from NLG systems. So what kind of data did we use for this task? We took Europarl and TED Talks, so spoken language corpora. We did not have or do not have, unfortunately, data that is transcripts of or speech-to-text output, for example, that and their corrected versions, so that we would be able to present training and test sets for that. So we had to go through a proxy where we said, okay, we do spoken language corpora.
Don, can I interrupt?
Yes, sure.
There is some remainder of Zoom overlaid over the screen.
Oh.
So.
Sorry, you mean this panel?
Yes, we see not the slides itself, but the entire screen of your Zoom meeting.
Oh dear.
Maybe you want to stop share and share only the window. Maybe you want to stop share and share only the window of the slide.
That's what I did, but apparently that wasn't enough. That's what I did, but apparently that wasn't enough. What about now?
Yeah, it's better. We still see your entire screen, so the entire browser, but it's okay.
Okay, but you can see the slides. I think that's the most important thing. All right. So, all right. So basically, we had 4 languages. The input, so English, German, French, and Italian. The input was this stream of tokens, as I said. And for task 1, you just put the label where sentence end is. And for task 2, you had a set of punctuation symbols that you actually had to predict within this stream. All right, so that was the data and the setup. Now, participation was we're quite happy with the turnout. So we had, for task 1, we had 6 participants. Um, Sorry about that. For task 2, we had 5. So thanks a lot for contributing and participating. And now for the interesting part, or the peculiar part as well. So the results, as you've seen from the website and the mails that we send, we have 3 winners for this task. For both task 1 and task 2, there were 3 participating systems that got extremely similar results across all languages. So that was kind of interesting to observe. Also on the test set, the surprise test set, so the TED Talk data, the results were very similar, with only minor variations in the F scores per language. So yeah, that was surprising. The same for subtask 2. We again had on the average F1 scores very similar results in terms of F scores. Even on the test set is near identical, or it's identical if you average the F scores. Yeah. So we sort of try to look at this from different angles and see whether we could somehow determine a winner, because everyone likes to have a winner. But there was no real good way of looking at this, and averaging of averages and their surroundings errors and stuff like that. So there wasn't really one clear winner, and that's why we decided this is a joint win for the 3 top ranking systems. Just very briefly, we saw a lot of use of transformers, as is to be expected to some degree, in the participation. So that's maybe also a reason why the results are that similar. We saw good results across for both tasks and across all languages. So the question is, can we assume that the problem is solved to some degree? Maybe that's something we can discuss a bit later. But then on the other hand, we also saw that if we move to out of domain data, so the surprise test set results, the performance drops significantly. So that's something to keep in mind. So, and I think about the future, we can talk at the end, and I've already taken up a lot of time. So I will stop my presentation and give the word to HTW plus 2K. You should be able to share your screen.
Okay, thank you very much. So you should see my screen and hear me. Okay, I see you nodding.
Yes.
Okay, great. Thank you very much. My name is Oliver Gur. I present the paper from our team, HTW plus T2K. We are the University of Applied Science Dresden, a team from this university, and Anne-Kathrin is representing their company, T2K Text to Knowledge in Dresden. So the name of our model is full stop, or the paper, multilingual deep models for punctuation prediction. So in case you have any questions, just write me a mail afterwards, or just ask. Yeah, what we did, we run a lot more experiments than that, but in the end, we found that transformers work the best. We fine-tuned, and we found that the underlying language model is very important or significant for the output or for the result of the final model. That's why we perform more or less a grid search about a lot of different language models or types of language models for all languages. We trained them on just 10% of the data to save some time, because this is a very costly process otherwise, and selected the best results and trained these models on 100% of the data. We found only minor differences between training the model on 10% and 100% of the data, especially for task 1. 10% seems almost to be sufficient. On task 2, the models, of course, this task is a bit harder. Yeah, they gained a bit performance on 100% of the data. So since the documents were a lot longer than the transformer's context window or input window, we divided our data into 512 token segments, except for Distelbert. This is only a 265 token model. And we used a 10%, 100 token overlap between these consecutive tasks. We found that this improves the final model's performance slightly. This acts as kind of a data augmentation and yeah, position invariance feature for the final model. Yeah, just the results. We were honestly a bit surprised that the multilingual model outperformed all monolingual models. So this was like also a surprise for us. And we trained an additional model, a monolingual German model with some augmented data and submitted this as the third model for our task. But this performed even worse than our just plain unaugmented multilingual models. The models performed all well on full stops and commas. But we had a major performance degradation on hyphens and colons, since they are in many cases optional and they don't follow or their rules aren't as strict as for full stops and commas. So we run a set of ablations and try to answer some questions. First is, what are the optimal hyperparameters for each model? Since we trained a lot of different architectures and base models, technically you would want to do a hyperparameter search for every model, but this is again very costly and time consuming. And therefore we compared an hyperparameter search for the Adam optimizer to just using Adafactor, which can internally adjust its learning rate and parameters, and therefore doesn't need or doesn't rely as much as hyperparameters on hyperparameter search as Adam. And the results showed that an optimized Adam is on par with just using Adafactor and the standard learning rate. So that's why we used Adafactor for all models and did not bother with any hyperparameter search. We also tested out what happens or on which layers the model tend to learn the features necessary for the task. So we removed the set of layers from the top. So we trained a model with just 3 bottom layers, with 6 bottom layers, 9 bottom layers, all 12 layers for a bird-based model, actually. And we found that it's possible to retain 99% of the performance by removing a quarter of the last layers, just using a 9-layer model. And since task 2 is a superset of task 1, where the labels are superset, we can also just use the task 2 model for task 1, and the performance only drops marginally. But since it was a competition, we just submitted 2 models. But technically, if you want to do any rebirth applications, it's sufficient to just train a task 2 model. Our key findings are that the type and amount of data used for pre-training has a significant impact on the model's performance. We compared 2 bird-based models for Italian, one trained with 13 gigabytes of text and one trained with 81 gigabytes of text. And the larger 81 gigabytes or model that was trained on the larger 81 gigabyte text set outperformed the other model by 5%. So this has a significant impact. Not every model architecture works equally well for every language. So we found that Electra works quite well, surprisingly well for German, but is for Italian and English works worse than a standard bird model. I suspect I suspected an issue here, but we trained it with different hyperparameters and found no technical problems, but the models did not perform well. So I don't know why. Both tasks benefited from a multilingual model, as I said, and multilingual training data, as XML Roberta outperformed all other languages. And especially Italian, again, benefited from the multilingual approach and improved the results about 2 percentage points of the F1 score. And as Don already said, these punctuation patterns look to be or seem to be domain specific, and since the performance of our task one model drops from 0.94% across all languages to 0.78% for the out of domain data. So to conclude our paper, the multilingual models outperformed our monolingual models, so this seems to be the way to go. So I'm very interested in your other findings. The 550 million parameters of this XML Roberta model is, on the other hand, costly to compute. So you see there's these robots on on the right side of the picture, and it's actually our robots where we wrote software from, and my PhD thesis is about building a voice interface for these models, for these robots, and therefore we need segmentation module that can actually segment the voice recordings or the voice transcriptions that the robots make. But if you run a 550 million parameter model on device that is computation and power limited, you run really quickly into issues. So working on the efficiency of this model is one of our next step. And as Don already said, for reword applications, I think we need to improve the out of domain performance of the model, and training on larger, more diversity data sets seems the way to go. Yeah, and one next step is for me actually within the next weeks to publish the model and the code on GitHub. So that's everything. Any questions?
Well, I had a question, if I may. Like you mentioned, your multilingual models work better than monolingual. I was curious if you had any comment or insight about why. For instance, is it about related to the linguistic universals or something similar?
No, not really. There's a paper from Müller. I think I linked it in the paper. Yeah, it is linked in the paper, and it said that multilingual models share common features for across languages on the lower layers, and this seems to be related with the with the features that we found on the layer pruning approach, where we said, okay, you can remove the top layer safely and retain a lot of the performance of the final model. So I guess the transformers are able to found basic relationships between basic language features across all languages. So, but again, I think there needs to be some more studies on this topic, why they work so well. I think it could be totally different for unrelated languages or less related languages like German and Finnish or something like this. I don't think that the model will gain.
Yeah, language from
retain as much
different
performance.
Language families.
Origins.
Yes, great, thanks.
Can I just make a question also? I didn't, and in the slides where you talked about task 1 and task 2, I didn't understood if you trained or you experimented with multitasking on both tasks.
No, we didn't do multitasking on both tasks. We trained 2 models for this, for our final submission. So we trained one task 1 model and one task 2 model. In the end, I just tried to map the task 2 labels or the labels of the task 2, the output results of the task 2 models to task 1 by saying, by removing, by just mapping the final output labels, and found that it works nearly equally well for task 1. So there's no need technically to train a task 1 label. There's only a minor performance difference.
Could we please go back to the results and like the internal models checks that you had? You see.
This or this? No, this. Okay.
The bigger one, the one with more results.
Yeah.
Yeah.
Yeah. Okay.
So one thing that I noticed is there's a huge performance difference between Camembert large and Camembert base. Did you have a check as to why?
No, I didn't check why, but Camembert large uses 3 times as much parameters as Camembert base, and therefore 2 to 5% points in performance are within what I would expect to improve the. You can compare it to the last line, the multilingual line. XML Roberta base and XML Roberta large. It's the same step. It's also 3 times the parameters. And it's almost the same performance gain. You see, it's from 91 to 93 and from 71 to 75. So it's almost the same. These models scale well with, or as others found, transformers scale well with the number of parameters. So it's, yeah, a safe bet to improve your performance is to throw more parameters on it with all the downsides that you have at inference times.
Cool. Then that brings me to my second point. You mainly experimented with Electra generators, not the discriminator model. And I suspect this is why you did not find that great performance with Electra. But that's
okay.
Because like there's a sort of grand setup between Electra and there's a generator and a discriminator, and in the paper it's mentioned that the discriminator is meant to work and the generator is, maybe it works, maybe it doesn't.
Okay, so yeah, I suspected that this performance was so bad, I suspected that I had some issue somewhere, but that's maybe the thing that I overlooked. Yeah, this would totally explain why these results are so bad.
Yeah,
no worries, that was good.
Yeah, so thanks a lot for the presentation and the questions. Maybe at the end of the session, we can continue these discussions. We're already a bit over time. This is why I would like to ask the team on point to start their presentation and to be within, let's say, 8 minutes if you can, and to be within, let's say, 8 minutes if you can manage to do that. Thanks a lot.
I'll start. Hello and welcome everyone. We are Team on Point from the University of Zurich, and we'll be presenting our submission to the Swiss Text 2021 Shared Test 2, Sentence and Punctuation Prediction in NLG text. So let's start by briefly describing the idea of what we did. We modeled the problem as a token classification task and solved it using various transformers architectures, similarly to what we have seen. For increased robustness, we used 4 models and then essentially assembled them for each language. We aim to solve the class imbalance and long document problem that is presented in the task, in the dataset of the task. And our optimization was focused on subtask 2. And for subtask 1, for our submission to subtask 1, we simply mapped the predictions of the models of subtask 2 to subtask 1. Transformers have been proven to be effective in multiple tasks. Through our experimentations on the dev set, the table on the right shows the models we decided to use in the ensemble for each language. We set up experiments with multiple transformers. This included more standard transformers like BERT, multilingual models like XLM Roberta, and slightly more peculiar models like Electra and MPNet. On the note, I would like to note that everything we will see is considered to be a base model. Not small, not large. We haven't experimented with those. Cool.
One of the best performing and less known models in our ensemble is Electra. So we decided to have a closer look at it. The authors of Electra aimed at improving efficiency of pre-training of transformer models. And they argue that BERT-like masked language models basically learn just from 15% of masked tokens. They need large training data sets, large amount of compute. But the Electra model instead is different pre-training task, namely replace token detection. It uses small original BERT masked language model as a generator of sentences. Then the output is forwarded into the larger discriminator, which predicts for every word if it is original or replaced word. And after the pre-training, the generator is discarded, and the final Electra model is the discriminator part. And this way, the model learns from the whole training set, not only from the masked tokens. And this approach results in the Electra paper of gain of the performance of 6 glue points over the small Electra over the small BERT model, and about 3 glue points for large Electra versus large BERT model. And it was interesting to see that for each language, the set of best performing models was different. However, Electra is the best performing single model for 3 of the languages: English, German, and Italian. After the initial experiment, we hypothesized that we can gain performance by combining predictions from different models. Therefore, we decided to ensemble the best performing models trained on subtask 2 via a majority vote ensembling. The basic idea is quite simple. The final prediction is the most voted label, but in case of a tie, we decided to choose less frequent labels. And this decision comes as a part of the solution of class imbalance problem. And because the F1 score suffered a lot from low performance of hyphen and colon. And also we decided to count votes for these undersampled punctuation marks twice to increase also the probability of their prediction. Okay, we can go next slide. Yes, and before the training, the ensemble models, we also have to tackle the problem of the long documents. In the Europar corpus, some of the texts contain up to 100,000 tokens. And this is a significant problem for transformers since they are limited to 512 characters usually, with some exceptions such as longformer, which can digest about 4,000 characters. So the simplest solution would be just to split sequences into chunks of the maximum sequence length and then combine the predictions after inference. However, this might be problematic since the individual sequences may suffer from context loss, and we hypothesize that this affects especially the beginning and the end of a sequence. However, we decided to use this approach during the training phase to speed up the training. And more sophisticated and somehow better solution is to split sequences in a sliding window manner so that the split chunks overlap. And after inference, some of the tokens at the beginning and at the end of each individual sequence are discarded. And we use this approach during the predictions. And our experiment showed that an overlap of 40 tokens with 20 outermost tokens discarded at each side worked best.
Yeah, so within the dev set, the hyphen and colon classes were underrepresented and had thus low performance, as we've heard before. So since the assessment of the system is the macro average of all the classes, the performance significantly relies on how well the system can actually perform on these minority classes. To solve or tackle this problem, we have added a model within the ensemble that is biased towards minority classes using weighted loss that basically trades recall for precision. This approach has improved recall by up to 17% in exchange for precision, as I said, and the respective F1 score for the minority class by up to 3% in relation to the depth set data and a single model. I would like to point out two things about our results. Firstly, the scores on the development set and the test set are quite similar, which may imply that we succeeded at preventing overfitting on the training data. And secondly, and this is somewhat bad news, the surprise test has done its job well. So performance on this set is significantly lower compared to the in-domain test set. So there is definitely room for improvement in terms of generalization for our ensemble models. Last but not least, what are our takeaways? First of all, not all transformers work similarly well with respect to a specific language. Here we try to use our intuition as a starting point. For instance, BERT seems to be a good baseline, so why not start with that model? However, intuition should not stay unproven and always challenged by experiments. And transformer, however powerful they may be, suffer from some shortcomings and are not a panacea. From our point of view and in the context of this shared task, this was mostly the limited sequence length. To get the best possible performance, such shortcomings should never be neglected. Then the data in the shared task is not spared from class imbalance, as this is usually the case. The previously discussed simple weighted loss has brought some performance improvement. As a side note, we think it would have been interesting to experiment with other techniques such as data augmentation. And lastly, we are happy to report that we achieved top performance on the average of all languages, so to speak, a multilingual setting for the in-domain test set and surprise test set. For both subtasks. And this concludes our presentation. Thanks for the attention, and also a big thanks to the organizers for this nice shared task. It has been a pleasure. And if there are any questions, we are glad to answer them.
Yes, thanks a lot for the presentation. Maybe we have time for one question, if there is one. If not, maybe at the end of this session, or sorry, Oliver, go ahead.
Thank you very much. I think I missed the point. Which models did you connect to an ensemble? Which did you use for your final ensemble?
This would be the models that you see here in the table. So 4 models per language, and
okay.
All right.
Thank you.
Just a comment about the organization. We're going to run over the 1 hour, but from the conference program, there is no immediate session after that. So I hope everyone is fine if we take a bit more time for the discussion of the workshop and maybe be done at 10:45. So then the next team would be on Babel. Then the next team would be on Babel.
Hello, everyone. Can everyone see the slides?
Yes, thank you.
Okay. So our paper submission is called the Multilingual Simultaneous Sentence Ends and Punctuation Prediction. I am Ricardo Rey. I'm a research engineer at Babel, and this work was jointly with Inés Lisboa, which is a research group from the University of Lisbon. So our motivation is basically at Babel we have a subtitling pipeline, and one of the problems that we face is that the MT system ends up doing a lot of translation errors because of the bad source input, and usually that source comes from an ASR, which doesn't do proper punctuation, and sometimes also the capitalization is very bad. So we want to improve this input in order for our translations to be better. And in order to do that, we worked for almost 1 year in these problems, the capitalization and punctuation prediction. It's a paper still under review, so we hope that it's going to be released in the end of the month. But we address this task as a sequence labeling task, where for the gaps between words, we want to predict if there is no punctuation mark, if there is a period like exclamation or a semicolon with the label P, and if there is some commas, colons, or dashes with the label C. And in our previous work, we showed that it's possible to train one single multilingual model for English, German, Dutch, Portuguese, and Romanian. We used TED Talks, and we compared these systems with monolingual baselines. And overall, we knew already that a multilingual model is very competitive versus the multilingual model. And I believe that also the multilingual model has the advantage of basically seeing more data, because you have twice or triple the size of the data if you are using three languages. So for this shared task, we actually only had to take the previous model and extend it for the two subtasks. And since we already had one model for all language, or at least we were planning on participating with one single model for all languages, we also decided to create one model for the two tasks. So we actually participated with one single model, a multilingual model, that instead of having one classification head, has two classification heads, one for the binary task and the other one for the multi-labeling task. And the difference between our model and some of the models that were also presented, I believe it's because we are not tagging the words itself, we are tagging the gap between words by concatenating two word embeddings. And we had some experiences in our previous work where we showed that this gives a good performance boost. Also, similar to what other participants noticed, the transformers layer, the different transformers layers don't give the same results. Some layers are more important than others. So we use a layer-wise attention mechanism, and we let the model learn which layers are more relevant to the task at hand. Okay, so also in our previous work, we mainly focused on XLM Roberta base. To achieve higher performances, we just replaced it to the large model. And also we had our parameters were super optimized for the TED Talks domain. So we wanted to also run an hyperparameter search to search for the best hyperparameters for the AeroParl data. That might have affected our surprise test results, but we didn't know at the time that it was TED Talks, because actually our previous work was all based on TED Talks. So this is the list of the models that we trained. the baseline is the simple model. It's the model from our previous work, which means that it's a XLMR base. This is a base model. And we noticed that the base model, just using the same parameters, but replacing the base model by the large model, we get a performance boost. Also, in here, you see the macro F1 is quite low, but it's because we never use the O label. We exclude this label. So we are only looking at the other labels. So basically replacing the base model by the large model gives us a boost, and then just running an hyperparameter search, we were able to find another set of hyperparameters that were able to give us another boost in terms of macro F1 while keeping the binary F1 at the same value. During the hyperparameter search, we were monitoring the macro multiplied by the binary, which more or less gives us as a balance between those two tasks. And yeah, that was our approach for the shared task, and we are happy to receive some questions. I have the code already in here. Wait, we already have the code and the model, the pre-trained model in our GitHub. You just have to switch to the shared task branch. And also, just a curiosity, the model learns to attend to the last two layers, which it's a different, it's basically counterintuitive. We always thought that since this is a more syntactical task, the model would attend to the first layers, but actually the model learns to ignore them and just attend to the last layers, except the last one, which is also an interesting result. Is there any question?
Yeah, so thanks a lot. That's actually quite interesting. And I think my main question would be, but maybe also we can talk about this at the end, about your experience with the TED Talk data in general. If you see, so we see a huge for all system drop when we move to TED Talks. And I was wondering whether the task itself is just more difficult on the TED data than on the Europarl data. So even if you would train an in-domain system on the TED data, you would still get lower results than from the Europarl. That's one thing I still want to try out, but I'm not sure whether you have some, or maybe you have some insight that you can share on that.
Yeah, definitely the TED Talks that it's more difficult. Like the results that we did some experiments in terms of we used Europarl before for doing capitalization, and we noticed that Europarl data is super easy to start overfitting the domain, because the way Europarl scripts were written, it's super it's not so spontaneous. So I believe that TED Talks are much harder, actually, because from TED Talks to TED Talks, you also switch the speaker. Our results overall, the results that we had before for TED Talks, were much lower than the ones we achieved for this shared task.
Okay, thanks. So thanks a lot. And if there are no more questions at this point, we would move to the next presentation, which is by OneNLP. At this point, we would move to the next presentation, which is by OneNLP.
Hi. So I am Pruthvik. I am going to present our work, Deep Contextual Punctuator for NLG text. So I am a PhD student, and I will be presenting this work with Vandan, one of my PhD colleagues, and we are from LTRC, IIIT Hyderabad in India, which is a research institute. So this is the outline, and then we will directly jump into our work. So this share task was a task where we uh, were tasked to uh, predict the sentence end and punctuations, and we applied different kinds of sequence to tag predictions, and our best performing models were multilingual BERT over all the languages. Uh, so, I will give you a very short introduction. So, usually ASR systems do not uh, provide any punctuation marks. That is uh, there, and a lot of so PDFs. If when we are converting from PDF to text, there are a lot of misplaced uh, sentence end markers. So there is a lot of requirement for punctuation prediction. So uh, this also has a very cascading effect. If punctuations are not handled properly, that will impact the downstream tasks like summarization, query answering, as well as machine translation. So most of the previous works were divided into three broad categories. People used speech related features like prosody, and lexical feature which used only text features. And nowadays people have started using BERT and all deep learning models. So coming to the data sets, so uh, the organizers did not provide the number of sentences and all. So what we did is like we took the subtask one labels and found out this. So subtask one is a binary prediction, and subtask two is a fine-grained prediction of individual punctuation marks. So, so it's a fairly big data sets uh, for all the languages, and we can see that the average sentence lengths are more or less 25, and so we tried different approaches, ML approaches as well as BERT approaches. So what we started with CRF based sequence to sequence prediction. So we started with English. So from the previous slide, we found out the average sentence length was 25. So what we did is like we fixed the sequence length to 25 for the CRF task. So we only used basic features without using any kind of external tools like POS tagger or parser. So we just used simple feature like window of words, uh, uh, where we considered the previous two words, current word, and next two words. So the next slides will be explained by my colleague.
Yeah,
Vandan.
hi. Yeah, so after CRF, we also explored the use of contextual embedding on directly with the multitask setting. So basically, as BERT or so here we use multilingual BERT and the Albert, and the last layer, softmax prediction layer would be divided across the two tasks, like first for the task set task one and the subtask two for the punctuation prediction. And yeah, so basically here we used Albert for the English mainly, and multilingual BERT for the other four languages. And so here if you see next slide please. Yeah, so if we compare the results across the task, uh, so CRF performs bit lower with due to obvious reasons, like due to limited context and all that. And so when we look at the BERT results, so here English we are using the Albert, and for other languages, other three languages, we are using multilingual BERT. uh, and surprisingly we see similar results, and for German the multilingual BERT is performing better across all in these settings. And this explores this is for the task 1, and this explores the discussion point like, yeah, obviously the CRF would be the inferior to the PERT due to the less context, and this will lead us to discussion for like we need to explore the different contextual embedding, either language specific or multilingual, where and why does it helps. Basically, if you notice, the Italian one would be the bit lower if we use multilingual BART compared to the German. So maybe because of the larger data that multilingual BART has for the German and compared to the Italian. So this suggests the point like, if some different contextual embedding with the limited data only for Italian, would it be better to get results through it? So that was the few discussion points that we had at the end, and yeah, this was the our result. That's it. Thanks a lot.
Any questions?
Okay, so I have one question. So for this, so I was excited to see that there's also people who tried at different things than transformers. For the CRF, I was wondering why did you only use 5 words for the context, which seems quite not that many. Did you try wider windows for the CRF?
So so this was like we consider only 5 because we in our previous experiments with most of the syntactic tasks we experimented with different kind of windows. So we found that the window length of 5 was the optimal one, but yes, we did not try with other window lengths. And we wanted to like build a very generic system. We did not use any kind of external tools because the performance of external tools like parsers, uh, the performance vary widely. So it may work well with English, but may not work better for other languages.
Okay, thanks. So if there are no further questions, we would move to the next team, which is URMSBD.
Yeah, moment. Moment. So. Great. Yeah, you should be able to see the slides now. Yeah, hello everyone. My name is Gregor Donabauer from Information Science at University of Regensburg, and yeah, I'm going to present our approach to this shared task at SwissText. We only participated in the full stop prediction task, and this was a joint work together with Udo Kruschwitz. So a short overview of this presentation. Yeah, maybe quick explanation what this team name means. So UR for University of Regensburg, M multilingual, and SPD sentence boundary detection. And what am I going to talk about during the next couple of minutes? First of all, we will have a look at our approach, especially pre and post processing, and also talk about the results, and finally having a short discussion and conclusion. So our approach is nothing spectacular. We use very simplistic approach. We also fine-tuned BERT models regarding this task. For, of course, token classification, you can say it's basically binary IO tagging. And surprisingly, compared to the other teams, we found out that, or could observe that language-specific models work better. And there was also this paper of last year, where this was stated in terms of especially low resource languages. So I guess if you talk about English or German models, there is not really a large difference between the multilingual model and the language-specific ones, because these are very high level resource languages. But if it comes to languages which are maybe less represented in the train corpora, the performance is dropping. And we observed this especially for Italian and French. That's also why we adopted language-specific models, as I said, and I also listed them up here below. And as you can see, of course, they are trained on monolingual corpus. So what we did now is use these pre-trained models and fine-tune them in 3 epochs with a batch size of 8, and we used the maximum sequence length of the BERT models. So basically also no overlapping. And maybe what is most interesting here is how we pre-process the files. So of course, we had as an input those tab separated value files, and we simply concatenated all of the tokens. So for example, in context of the English test set, or whichever set you want to imagine. And while reading those files, we also saved the order of the files as we read them, and also how many tokens, word tokens are available in each file, which will make it possible for us to restore the TSV files later. And now we use this word token list and feed it for pre-processing through the model tokenizer. And of course, the word-specific tokens differ from the word tokens. And we simply count those word-specific tokens at each word token. So for example, here I wrote up the word embedding, and this consists of 3 word-specific tokens. And we create samples of as much tokens as possible. But of course, it is not guaranteed that we always have those 512 tokens exactly if we use those words. And that's why we padded the last positions of some of the samples, of course. Yeah, right. And then you can use those samples to train, evaluate, and test. And if we get the predictions, we simply reconcatenate those word tokens and predictions. And with the dictionary where we save the file order and number of tokens, we can restore the tab separated value files. Right. So that's basically our approach. And we rank 4th of the 6 submissions, and we are lagging only 1% behind the winner teams regarding overall F1 scores. And of course, we could outperform the SPACY baselines by a large margin. And as you can see, for German, French, and Italian, only 1% F1 behind the winner or the best performing team, and in terms of English 2%, but overall, as I said, only 1%. Yeah, some final words for discussion. So we could again demonstrate that our approach is highly competitive, even if it's very simplistic, and we have experimented with sentence boundary detection before. And as also stated by the other participants, if the train and development sets are representative for the test set, we can obtain similar results. But for this surprise test sets, where we have out of domain data, the performance is dropping in our case from 74 to 80% F1 compared to this high 90% plus region scores. But it's still a solid performance in our opinion. And as I said, we have worked on similar problems before. And for all of you who are interested, we want to invite you to test your system performance on other data sets also. And that's why we link your GitHub here. Right. So that's basically everything. Feel free to ask any questions if you have one. And thanks a lot for your attention.
Thank you very much.
I have one question.
Yeah, sure.
So when you're counting the maximum sequence length, why the so can you go to the slide where you are counting the so why token count +3?
Yeah, that's in this example, as I said, we have the word embedding here, and embedding is split into these 3 tokens. As you can see here, a token count +3 is because you have only one word embedding here. So embedding did not a word embedding, but the word embedding. So it's maybe a little bit complicated example, but yeah, this word consists of 3 bird-specific tokens, and for the example I added 3. But of course, you have to add the number of bird-specific tokens at this word.
Okay, thank you.
May I ask another question?
Yeah, sure.
Do you remember how much time does it take to train and for training and inference? Do you remember the time that the model required to process your data?
You mean for post-processing or whole training process?
No, just for training and inference time. I mean, how much time does it take to?
So we ran that on 3 GPUs with 33 gigabyte computing capacity, and this took, I guess, about 30 minutes per epoch. So overall, as we ran it in 3 epochs, 1.5 hours. Yeah.
That's for training, and this is similar for inference?
No, that went faster. So I guess it took 20 minutes only for inference. Yeah. So
okay.
for the whole set.
Great, thank you.
Yeah, you're welcome.
All right, so then let's move on to the presentation of the team Hulat. I hope I pronounced that correctly.
Yes.
Thank you. That correctly?
Yes.
Thank you.
Let me, okay, I don't know. Can you see my screen?
Yes.
Okay. Hello, everyone. My name is José Luis López, and I am part of the Hewlett group. I am here on behalf of my partners, José Manuel Maciello and Paloma Martinez. I am going to describe our approach for this task. Okay, this is a simple approach to. We know that ESR transcription is a difficult task. We set up the punctuator framework, training and configuring the recognition of punctuation marks according to the competition. Our aim is to explore results of this kind of systems, especially in Spanish, but we took the competition as a way to get into this world. Basically, we set up the punctuator system. We first of all train the punctuator with the training dataset of the competition, adapting the input and training the system, and then we evaluate with the different languages. And this is our experiment setup and the preprocessing. Basically, and the results, okay, in English are around 84% in the best case of English. Surprisingly, the results slightly improves in subtask dogs, subtask 2. This is the confusion matrix for the second subtask. The system is based on a LSTM network, and we trained it according to the recommended parameters of 256 hidden layers and a learning rate of 0.02. Our best result is of 84% in F1, and the worst result was in the German language. And as I said before, in subtask 2, the results improved, but we don't know exactly why this result was better in the second task. Future work, we are planning to use Beator, the Spanish version of BERT, and include other non-lexical features like pause and the length of the pause of the sound in order to improve the results. This is our approach, have very fast presentation. If you have any questions, I'll be glad to answer your questions. Okay, thank you very much.
All right, thanks a lot for the presentation. Are there any questions?
I have a short question.
Yeah, sure.
Why do you think that the model performed relatively well for German, but worse for all the other languages? Have you explanation for that?
No, we have no an explanation. We train separate models for each language. Surprisingly, for the first task, the results of the German language was the worst one, and surprisingly, in the second model for the second subtask, the results improved. But we are investigating why, but we don't know. We don't know why we obtained this better performance in the second subtask.
Okay, great, thanks.
Thank you.
Okay, so yeah, just from my side, I was very happy to see that someone made the submission using Punctuator, because actually Punctuator somehow completely slipped my radar when I was investigating this and setting up the share task. So I thought it would have been a very good baseline also. So yeah, but and it also involved a lot of work that we actually sort of replicate here. So the original punctuated paper also uses Europarl and TED Talk data. So yeah, it was interesting to find out about this a bit late in the in organizing the share task actually. But thank you for trying out Punctuator on the data. So that's great.
You're welcome.